Today, we're diving into a seismic shift in robotics, moving away from single-purpose machines towards a future where one robot can learn many skills. Arjun, this page asks a fundamental question that's reshaping the entire field. Can such a consolidation happen in robotics?
Historically, every new robotic task meant retraining or even redesigning systems from scratch. The vision here is a single, adaptable brain for diverse physical forms, a true generalist that can learn and apply knowledge broadly.
The core concept is this generalist X-robot policy that can be adapted efficiently. This isn't just about controlling one type of robot. It's about a unified policy capable of transferring knowledge across entirely different hardware and tasks.
So one core model for potentially all robots? That sounds incredibly ambitious and efficient compared to current methods, which often require bespoke solutions for each new application.
Achieving this generalist capability requires massive data diversity. This project pooled experience from 22 different robots, collected through a collaboration between 21 institutions. That's not just data, it's a collective, standardized effort to build a foundational dataset.
22 different robots and 21 institutions? That's the kind of collaborative horsepower you need to tackle a challenge this big. It feels like a Manhattan Project for robotics data.
The model, dubbed RTX, trained on this vast dataset, shows a crucial property. It exhibits positive transfer and improves capabilities. This means knowledge gained on one robot actually helps another robot perform better, even on different tasks.
That's huge. It's like a human learning to ride a bicycle and then finding it much easier to learn to ride a scooter or motorcycle. The underlying principles transfer, accelerating new skill acquisition. For builders, how does this ability to explore this possibility in the context of robotic manipulation change their approach? Is it about faster deployment or enabling entirely new, complex applications?
It means developers could take a pre-trained RTX model, fine-tune it with minimal new data for their specific robot, and achieve competent performance much faster than training from scratch. It dramatically lowers the barrier to entry for complex manipulation tasks.
Wait, look at this. It's the largest open-source real robot dataset to date. That's not just big, it's a game changer for accessibility, isn't it? It democratizes access to diverse, real-world robot interactions.
Absolutely. Historically, collecting diverse robot data was a huge bottleneck. This open-source release makes high-quality interaction data available to many researchers, greatly accelerating progress across the board in embodied AI.
This open-source data foundation is truly enabling. It's making generalist robot models possible. Now, let's look at how they actually built these models, RT1X and RT2X, and what makes their architectures unique.
We'll dive into the specific architectures and how they leverage different learning paradigms, from efficient transformers to large vision language models, to achieve these results.
So, moving from the main project page, we're now on Hugging Face, looking at an open X-Embodiment dataset, an official entry. It's an unofficial wrapper, but it makes the data incredibly accessible, doesn't it, Arjun?
Yes, this Hugging Face repository is critical for adoption. It wraps the raw data in a user-friendly format, allowing researchers to load dataset with just a few lines of Python, streamlining experimentation significantly.
What's powerful here is the list of optional sub-datasets. Fractal 2022-0817_data, KUKA, Bridge, and many more. It really underscores the massive effort involved, bringing together named datasets from many different labs.
Seeing all these individual contributions listed here, like Berkeley cable routing or Stanford KUKA multimodal dataset, truly drives home the scope of this aggregation and the community collaboration.
Back on the main site, they specify how they train two models on the robotics data mixture.
These are RT1, an efficient transformer, and RT2, a large vision language model. This bifurcated approach is strategic.
So, one is a pure control transformer, optimized for efficiency, and the other integrates language, perhaps to interpret higher-level, more abstract human commands. That sounds like a powerful combination.
Precisely. RT2X, building on the RT2, a large vision language model co-fine-tuned paradigm, is particularly interesting. It learns to output robot actions as natural language tokens, which means it can potentially understand more abstract instructions.
This is a big step towards more intuitive human-robot interaction. It moves beyond explicit joint commands to something closer to how we communicate intent, allowing for more natural interfaces.
This approach, having the model output robot actions as natural language tokens, mirrors a trend we've seen in pure language models. They're essentially applying lessons from LLMs to the embodied domain, allowing for more compositional and generalized behavior.
It's like giving the robot a vocabulary for movement, not just a set of physical coordinates. That's a clever way to bridge the gap between high-level thought and the concrete actions a robot needs to perform.
The actual physical output, regardless of the model type, is quite precise. The robot action is a 7-dimensional vector. This defines the full pose and state of a typical robotic arm's end effector, including position, orientation, and gripper state.
So, despite the high-level language input for RT2X, the physical output still translates into these fundamental continuous control variables. It's a comprehensive bridge from abstraction to concrete motion. Okay, we've seen the data scale, the model types, and how actions are represented. But what's truly exciting are the capabilities these models unlock. Let's dig into the emergent skills that RT2X demonstrates on the next page.
This is where the generalist approach truly shines, showing behaviors not explicitly programmed, but learned through broad exposure and the ability to generalize across tasks and embodiments.
All right, we're on the GitHub repository for open X-Embodiment, which states its goal is to provide all open-sourced robotic data in the same unified format. This is where developers will actually get their hands dirty, right, Arjun?
Precisely. This repository is the direct interface for practical implementation. It standardizes data formats, which is crucial for interoperability and for fostering a larger collaborative development ecosystem around these models. A key mechanism here is that the model takes an RGB image and a task string describing the task. This task string is how the human communicates the goal to the robot, directly leveraging the vision language capabilities we just discussed.
So you don't program a sequence of movements, you just tell it, pick up the red block? That's a huge shift in how we interact with robots, moving towards more intuitive instruction.
And importantly, small changes in preposition in the task string can significantly modulate low-level robot behavior. This implies a sophisticated understanding of natural language, where subtle linguistic cues translate directly to nuanced physical actions.
That's incredible. It means the model isn't just parsing keywords, it's genuinely interpreting the semantic meaning of the instruction to refine its movements, showing a deeper comprehension.
This phrase, RT2X, demonstrates skills that the RT2 model was not capable of previously, truly gets at the emergent capabilities in our episode title. What exactly does emergent mean in this context, Arjun?
It means the system developed these abilities, like inferring complex spatial relationships, not through explicit programming for that skill, but as a byproduct of training on a vast, diverse data set. It's a leap beyond what was directly taught.
For a builder, this ability to have a task communicated to the model purely through the task string fundamentally changes the development paradigm. It's less about coding motion primitives and more about crafting precise natural language prompts.
Indeed, it transforms robot programming into prompt engineering. Developers can iterate on task descriptions much faster than on control code, accelerating the development of new applications and fine-tuning existing ones for subtle variations. It's important to note the current input limitations. The model currently does not take in additional camera images, such as wrist-mounted or in-hand cameras. It relies solely on a single RGB workspace camera view.
That's surprising given the dexterity it achieves. It suggests the model is extracting a remarkable amount of information from that one view, or it implies future upgrades will unlock even greater precision and capability.
The concept of emergent abilities is central to foundation models. It's what allows these systems to generalize. But how well do we really understand where these abilities come from? Let's look at some recent research trying to explain this phenomenon.
It sounds like we're moving from what they do to how they do it, which is crucial for building even more capable and predictable systems. We've seen RTX demonstrate emergent skills. But what is emergence? This paper, Understanding Emergent Abilities of Language Models from the Loss Perspective, tackles exactly that question, and even critiques some common beliefs about it.
This research offers a more rigorous lens, moving beyond anecdotal observations to a quantitative understanding of when and why these unexpected capabilities arise in large models, specifically here within the context of language models. The paper starts by challenging a prevailing belief that emergent abilities in language models are exclusive to large models. They found smaller models can exhibit similar performance, suggesting model size isn't the only or even primary factor.
That's a provocative finding. It shifts the focus from sheer scale to other underlying mechanisms, which is important for resource-constrained development and could democratize access to these advanced capabilities.
Instead of model size, they study emergent abilities in the lens of pre-training loss. This means focusing on how well the model predicts its next token during training, rather than just how large the model is or how much compute was used.
So it's not just about how many parameters, but how effectively the model learns the underlying patterns during its foundational training. This feels like a more fundamental measure of learning efficiency.
They discovered that a model exhibits emergent abilities on certain tasks, specifically when its pre-training loss falls below a certain threshold. Before this point, performance is effectively random guessing. This threshold is a critical insight, revealing a phase change.
This isn't a gradual improvement then. It's a sudden phase transition. It's like water boiling. You hit a certain temperature and the state completely changes, even if the input changes smoothly and gradually. If these abilities cannot be predicted by merely extrapolating past performance, what does this mean for developing future robot foundation models like RTX? Does it make progress harder to forecast or guarantee?
It suggests that simply scaling up existing models might not guarantee new emergent capabilities. Researchers need to actively push the pre-training loss below these identified thresholds, which may require architectural innovations or more efficient learning strategies, not just larger models.
So they actually redefine emergent abilities as those that manifest at lower pre-training losses. This isn't just an observation. It's a new, more precise working definition. That's a strong statement for the field.
Yes, this redefinition is crucial. It provides a testable hypothesis for emergent behavior, shifting it from a qualitative observation to a quantitative metric tied directly to the learning process itself, making it more scientific.
This research really deepens our understanding of the magic behind generalist models like RTX, showing it's not just size, but how effectively they learn. It's an exciting and rapidly evolving time to be watching robotics.
The journey towards truly embodied artificial intelligence is complex, but with these insights,
We're building a clear path forward for dexterity and task transfer.
I'm Arjun. And I'm Maya. See you next time on the Clue Matrix.